Now we could get an analytical version of that, but I really want to use this as an example so that we can figure out how to do the system dynamics. So this is all stuff that we're going to take as a given. We've got this Q function. Now let's go use it. We're looking for a flow transient, and we're going to use Euler's method to predict transient level changes. So if we do that balance that we talked about before on tank A, then the volume in tank A is going to increase or decrease based on how much flow is coming in and how much flow is going out. So the change in the volume in the tank with time in cubic meters per second is the flow rate in cubic meters per second coming in through the tap minus the flow rate going out through the tube between A and B, again in cubic meters per second. So that gives us a rate of change of the volume of water that's in the tank. Now the volume of water in the tank is the height times the cross-sectional area of the tank. So if we divide by the cross-sectional area of tank A, then we'll get the rate of change of height in the tank with time equal to the difference between the flow rates divided by the cross-sectional area. So the smaller the cross-sectional area, the faster the height will rise. And if we look back at tank A, we've got multiple different cases here. We could have the water on both sides below the pipe, in which case nothing's going to flow. We could have the water in A above the pipe, in which case it's going to depend on how much it's above the pipe, how much flows through the pipe, and it'll pour off the end and down here. We could have both of them above the pipe, in which case it'll just depend on the difference in levels between tank A and tank B. And if it got to here, they would eventually equalize with both at the same level. If we, so those are the cases we've got. Let's have a look at them. Both below the tube, no flow. The tank A is above, so the flow depends on HA. Oh, there's another one that we didn't talk about. Tank B is above, but tank A is below, so the flow only depends on the height in tank B. Now in this particular configuration, that's not going to happen because we've got the tap filling up tank A. But we'll consider it as part of the general case. So let's assume the bottom of tank A is at 3 meters above some datum, and the tube's a little higher at 3.1 meters. That gives us a reference level for all of our heights. And tank B, the bottom is a little lower at 2.5 meters. And for now, we're going to ignore tank C. We can calculate the flow rates at the current time step, and then advance the tank levels, because tank levels are going to change over time using Euler's method for each of the tanks. So if the flow from the tap is fixed, then sometimes it'll be larger than the outflow, and maybe even all the time if we set it quite high. So the height in tank A at time t plus delta t will be whatever the height in tank A was at time t plus the rate of change of the height in tank A with time times delta t. That's a linear first order approximation. That's Euler's method. It's not the best numerical technique, but it's going to work for an awful lot of things. And if we substitute in our expression for the rate of change of height, it'll just be the height that it was in the tank plus the difference in flow rates divided by the area times delta t. So as long as you've got a differential equation for each of the elements in this system, each of the tanks, you can solve for as many different interacting elements as you want. So that's kind of cool. So let's start off our simulation and see where it takes us. If I start off by saying that my tap is flowing about 1 beverage can per second, or about 0.000354 cubic meters per second, and I'm going to go for 500 time steps at 1 second at a time, so about 1 beverage can of flow worth each time step. I can set up a linear space in time going from 0 up to 500 steps times the time step, and I'll make it 500 steps long. I can say that HA, the height in tank A, is going to have n different values at the different time steps, and I'll start off by making them zeros, and I'll make HA at time 0 equal to 3, the bottom of the tank, so we'll assume it was empty. I'll do the same for HB. I'll assume it's empty and its bottom is 2.5. And the flow from A to B, I also need to keep track of how it changes with time. So I'll have another space that I can put those values into. And finally, the tap, I'm going to say that the flow coming in from the tap is a vector of n values, and it's going to start off with all of them equal to Q tap. So 1 beverage can per second. Cross-sectional areas, I need to pick something, so I'll pick a 20 by 20 centimeter tank. So it'll be a 0.04 square meter cross-sectional area. The tube, I'll keep at the 1 centimeter diameter, and the length of the tube I'll keep at 1 meter. And I'll set that to be the same value for all the tanks, just to avoid complexity. We could easily make an array of different values for all the tanks if they were all different shape, but they look the same in the picture. So now I'm going to go through all the time steps with a for loop that goes from time 0 up to the last time step. I'm going to fill in the blanks and then calculate new values. So first off, I've got to check what's going on with tanks A and B. So if tank A is less than 3.1, it's not up to the tube. And if tank B is also less than 3.1, it's not up to the tube. So the flow rate's going to be 0. If tank A is less than 3.1 and tank B is more than 3.1, then the flow rate's going to depend on the elevation difference between the tube and the height of tank B and the length and diameter. So this is going to wind up being 3.1 minus HB. That'll actually be a negative number, and the flow rate will go backwards from B to A. I don't think that's ever going to happen, but I built it into my code. If the height of A is greater than or equal to 3.1, then if the height of B is less than the tube height of 3.1, then the flow rate is going to be the amount that tank A is above the tube, and it'll have no effect on what the level is in tank B. Likewise, if tank A is above 3.1 and tank B is above 3.1, then the flow rate is going to depend on the differences between the levels in the two tanks. So once we've figured out the flow rate between A and B, and we know the flow rate coming out of the tap, we're ready to calculate the change in the height of A, the value it'll have at the new time, by taking the value it had at the old time and multiplying it by and adding the derivative multiplied by delta T. We can also get the height in tank B by taking the original height in tank B, multiplying it times the derivative for tank B, which is just going to be the flow rate coming in from pipe A and B, ignoring the pipe going out to C for now, times delta T. We can plot those values then and see what's going on. So let's run this one. And here I see the plot of the values. Let's try to interpret what's going on here. Tank A, the height starts rising, and then it's not rising as quickly. That's because when it gets to 3.1 here, water starts pouring into tank B, and tank B starts rising. And there's a transient in here, but eventually they catch up. And then they just keep on filling. And tank B is always a little lower than tank A because there has to be some flow in between them for the dynamics. So there's this interesting startup phase, and then there's this final stable phase where there's water sort of flowing downhill, and there's a lower elevation in tank B than in tank A. But wait, up here, tank A has a top, so it's going to overflow. Tank B has a top, so it's going to overflow eventually. So we better account for that. So in here, we were just going to let the heights go up indefinitely because we said that the height, the new height, was going to be the old height plus whatever the flow was. But if we want to account for the flow that's just pouring over the edges, then we'll have to account for the fact that the height can never get taller than the rim. So I'm going to do the same thing again. And I'll add in tank C. So this time I'm taking some more time steps, but I'm keeping the rest the same. And I'm defining this function called calcplot. Basically just all the same calculation, but putting it in a function so it's easy to call. So all the same stuff going on here. We set up all the values for HA, HB, HC. We get some variables to put the values for the flow AB and the flow BC in as we go along. We've got our flow from the tap, and then we're going to go through all of the steps. We've got exactly the same as we had before for the flow going between HA and HB. We wind up getting QB, and we know what the flow rate is through the tube. So now we'll get the flow rate going from B to C. And it depends on the difference between the height in tank B and the height in tank C. And it has different levels. The pipe in tank C, let's say it's at 2.6 meters, whereas the pipe in tank A was at 3.1 meters. But otherwise, exactly the same thing. We've got the height in tank A. Well, this is the same equation we had before, but now we're going to say it's the minimum of either that height or 3.5, the top of the tank. And B, likewise, it'll be either the amount that we get by following Euler's method or the tank's full and it overflows. Tank C, the height that we get by following Euler's method, or the top of the tank and it overflows. So now we can plot the values and see what comes out if we run this function. It's a little long and tedious, but the concepts are really pretty simple. And here's what comes out. Tank A is filling the way it was before and eventually overflows at 3.5 meters. Tank B doesn't start filling until we get up to 3.1 meters, and then it starts filling, and when it gets up to the height for the 2.7 meters, where it starts overflowing into tank C, then tank C starts filling up. And because tank C has no outlet, it eventually fills and overflows too. But what's interesting to notice is that tank B, with an outlet and an inlet, doesn't actually ever get to its full, to the brim height of 3.2 meters. It only gets up to about 3.1 meters. So it allows us to have an equilibrium in here where tank B doesn't overflow, even though tank A and tank C do. That's kind of interesting. So we can watch that progress, and we could try different possibilities. So let's consider the case, for example, where the flow from the tap is way smaller. That was the case that we were doing in the original puzzle. We were assuming everything was happening slowly, and let's see if it gives us the kind of solution that the puzzle makers expected. And sure enough, if I run this cell and do the calculation again, all I've done is I've changed the tap value down from 0.3 to 0.1. Now the flow is pretty low. Tank A starts filling up, tank B starts filling up, tank C starts filling up, and tank C is the only one that actually gets to be full. Tank A and tank B, they only get to be a little bit above the tube outlet. So we can do a whole lot of different simulations with this, and we can stretch this out to allow for all of the tanks, and we would find that the behavior of the system really depends on what the flow is that's going in. So let's try it with a higher flow. If we go up to 3 beverage cans per second and run the same thing, we see that tank A fills really quickly and overflows. Tank B, still winding up somewhere in the middle there, and eventually overflowing. And tank C also filling really quickly and overflowing. Now we've got a time step here of 10 seconds, and it seems to work. Let's check our time step and see what happens if we take a shorter time step. It just stretches out the behavior a little longer so we can see it in more detail. So let's go to 2. And it doesn't look like the behavior is that much different with different time steps. Let's go to 100. We've got some strange instabilities here, a little bit of bouncing. Let's go to 1,000. And the calculation breaks and fails. Obviously, it's not going to oscillate up and down like this. So we need to make sure when we're choosing time steps that we choose a small enough time step to make the calculation work. So that's the essence of simulating one of these systems with Euler's method. We can do as many tanks as we want. You can do the rest of the tanks if you like. And we can track how each of them changes with time. And the way each one of them changes with time is going to affect how much flow is going from one to another. And that will change the results for the other tank as well. So we need to simulate them in parallel like this. And this technique that we've got in our code up here is really straightforward. You can implement it for any function you want. So we really didn't need to know what the function Q was. We just need to have it exist. We can then calculate what the current state is for everything and predict what the new levels in the tanks will be based on knowing the derivatives from the flow rates. And you can apply that to a wide variety of different problems. So later on this week, we're going to simulate this kind of problem in your homework assignment. So you'll want to look back at this to see how it works.